Okay, hi everyone. Mike's a little loud today. So we're going to continue today with our discussion of neural networks. So this is part 4 of neural networks starting today. So as always, a couple of brief announcements before we get started. So the first is the third homework for the course is due Friday of this week. So in today's lecture, we're going to be taking a bit of a closer look at this assignment, giving you some hints on how you might approach some of the problems there. But it is due at the end of this week. Is a little bit shorter because of the midterm, but yeah, I encourage you guys to start looking at that soon. Also, just a reminder that the course projects are coming up sooner rather than later. So there is a team formation component to this project, so you guys should be getting into groups of 3 students. And this team formation is due in 2 weeks, so Friday, May 19th. It's a free 10% of your project grade to just have a team formed by this deadline, so yeah, make sure you're using that Team Finder spreadsheet if you don't have a team yet. And another announcement that we'll look at in the next few slides is the course survey that I sent out a few weeks ago. So 133 out of 162 of the students in this class actually responded, which is great. So thank you very much. We really appreciate your feedback. And so we'll be sure to sort of incorporate some of the comments you guys made into the rest of the quarter. So I always thought it was fun when my professor showed me, surveys and breakdowns like this. So here are just some anonymous statistics about that course survey that a lot of you guys took. So this first column here are essentially some statistics about the lectures. Overall, about, 90% of people think the lectures are more or less on pace, which is good. So people think they're clear enough, about just right in the pacing, and a good amount of questions, which is cool. So won't have to change the lectures too much. About 80% of people think the homeworks are just fine, and there's some people who think that they could be a little clearer or a little more well integrated with the lectures. So we'll definitely keep that in mind for future homeworks going forwards. And then the last 3 sort of survey questions here about the discussion sections, that probability review we did, and the math in the course. So about 70% of people are satisfied with the discussion sections. Something like 24% of people disagree that the discussion sections are useful. So I agree the discussions could be improved a little bit, and we'll think about ways we can make these better for you guys going forwards. I'm glad to see people enjoyed the review lecture on probability, and it wasn't sort of too basic. So for future quarters, this is good to know. We'll probably keep this in the lectures. And then this question was interesting. About half the people think that the balance between the math theory and the sort of hands-on applications is good. And the other half of people think that more hands-on practical details would be great. And I'm sorry to the 4 students who would prefer more math in the course. Looks like that's probably not going to happen. When I first started learning machine learning, I was one of these 4 students, so my lectures might be a little biased towards the math side. But going forward, we'll definitely do more sort of practical coding examples in lectures. So it sounds like that would be useful for you guys. Okay, and then in terms of sort of the free response, open-ended feedback questions, some common suggestions and comments we got are more hands-on coding examples in lectures. So yeah, we'll definitely be seeing some of that starting today. And just better connecting sort of the theory we see in lecture to the practice in the homework. Another comment we got a few times was just slower pacing on the sections which are heavy on the math, so totally can do that. And the last comment we saw quite a few times was that the homeworks are kind of scavenger hunts in the documentation for scikit-learn and matplotlib and so on and so forth. And I totally agree, but this is a pretty good simulation of what it's like to actually do machine learning in the real world. You know the models pretty well, you know what you want to do, but it's a matter of figuring out how to actually do that. So I'm somewhat glad we got this comment because that means that the homeworks are working as intended. So by the end of this quarter, you should hopefully all be pretty familiar with matplotlib, scikit-learn, these kinds of things, and can really navigate your way through the documentation and use the things that you've learned how to use. So cool. Again, thanks for the feedback. Very useful. So in today's lecture, we're going to start with just a recap of neural networks, just get a pretty broad overview of everything we've talked about so far. After that, we'll be looking at neural networks in code, so how do you actually implement a neural network? And in the last part of today's lecture, we'll look at some practical details of hyperparameter selection and tuning, and really kind of getting out the best possible performance from these models. Okay, So to summarize, what is a neural network? It's some big nonlinear function, f, that takes in a data point x and has a whole bunch of parameters theta. So just like every other model we've seen in this course, you can kind of abstract away the details if you like and just think it's some function that takes in data and spits out some kind of classification. The parameters theta in a neural network, it's now a very big parameter vector corresponding to all of the weight matrices and all of the bias terms in our network. So sort of all the weights on all of the connections in these giant networks. For a feed-forward neural network, or a multi-layer perceptron, which is what we've been working with so far, you have sort of these layers of weight matrices. And in between these linear layers, you have sort of nonlinearities. And these let you compute sort of the hidden units in your network. In terms of which nonlinear functions you typically use in a network, the most standard choice is this ReLU function, so essentially turns all the negative components of a vector to 0 and leaves all the other components alone. But you could use something like a logistic nonlinearity, or there's hundreds of other choices you could stick in here. And at the very end of the day, if we're doing a k-way classification problem, so we have k distinct classes in our problem, we apply the softmax nonlinearity in our very final layer so that we get out probabilities from our neural network. So very similar to a logistic classifier, we've just got now multiple layers of computation going on. And a little bit later on, we'll see sort of deeper neural networks. What we really mean by a deep neural network is just a neural network with multiple hidden layers. So the depth kind of corresponds to how many layers you have in the network. And then if you hear the terminology width, that's how many hidden units are in each layer. So a good picture to keep in mind is this sort of layer-wise or block-wise diagram, where you have your inputs, which are some vector of features x. Got some weight matrix W1 that allows us to compute the first hidden layer in our network. It's some vector of hidden unit activations. Got a second layer of weights, so on and so forth, till we get to our final layer, W sub L. And from these final hidden units, we use our final weight matrix, which we'll call beta in this course, and then apply the softmax function to obtain these output probabilities. And again, we have one output per class in our problem, where, say, f1 of x is what's my model's predicted probability for the first class, y equals 1, given my input x. So it predicts a class probability for every single input we give to this network. If you have just a single class in your classification problem, typically we just have a single output from our neural network. So this is similar to like a logistic classifier where we just predict a single probability corresponding to the class y equals 1. But for more than two classes, we'll have the number of outputs equal to the number of classes. And this architecture, this model diagram I'm showing here, is typically known as a fully connected neural network or a feed-forward network or multi-layer perceptron. Tons of different names, but this is kind of the most basic neural network architecture we'll see. Okay, so here's an example of what an actual neural network kind of looks like. You've got 7 inputs in this diagram, so we've got 7 features in our problem. We've got 3 hidden layers, so first hidden layer, second hidden layer, third hidden layer. And it's fully connected in the sense that between every node in sort of consecutive layers, we've got some edge connecting them, and we have some weight associated with these edges. We've got 12 outputs, so this is a classification problem with 12 classes. To actually train a neural network to fit it to data, what we need to do is use gradient descent. So this is our go-to optimization algorithm for most machine learning problems. And in order to get gradients for our network, i.e. the derivatives of the loss with respect to each of our parameters, we don't want to do this by hand. It's a very hard calculus problem. It wouldn't be fun. And so instead, we're going to use this algorithm called backpropagation, kind of glossed over the details. But the idea is that we kind of propagate information from the output of our network through each layer in order to get these gradients. So if you want to learn more about backprop, check out some links on that Canvas calendar. We introduced another optimization algorithm called stochastic gradient descent. And the idea in stochastic gradient descent is that rather than using all of the data points to compute the gradients, we're just going to use a small mini batch, a small subset of data to compute those gradients. And it's a sort of noisy approximation to the true gradient that allows you to get faster sort of real-time convergence. We'll see some more examples of this in a minute. You might be wondering, since neural networks are so great, they're all the rage, very popular nowadays, why don't we just use them on every problem? Like, why did I teach you about KNN and logistic models and nearest centroids? Why isn't this just neural networks, the class? And the answer is that neural networks really only work well when you have a very large training data set. So because there's so many parameters, there's so many sort of knobs to tune in these models, if we don't have enough data, we're just going to overfit, you know? We have 100 data points and 1 million parameters. Well, of course we can get 0% training error, and it's just not going to generalize. So neural networks are really only practical when you have enough training data to accurately fit these models. For example, huge neural networks, you know, the modern ones you probably hear about, like ChatGPT, so on and so forth, are trained on absolutely massive scales of data. So like ChatGPT is trained on more or less the entirety of the internet, at least the text. So that should give you a sense of how much data you really need to fit these models. And another sort of intuition you should keep in mind for when a neural network is going to be useful for your problem is when some sort of feature extraction is going to be useful. So this is generally when you have some sort of perceptual problem, so things like vision or speech or text, where you'd really like to take some sort of low-level input, like pixels in an image, and extract out some higher-level representation that you can do classification on top of. So this idea of representation learning is a really good sort of mental model for what neural networks are doing and how they work. So you can think of sort of all the hidden layers in your network as a sort of feature extractor. It's taking your low-level signal, like an image or something like that, and pulling out features. It's learning to extract features. At the very end of it, we just apply a logistic classifier on top of these sort of learned features. So it's one way of sort of taking my data and learning a new representation of it. Okay, so any questions on this high-level recap of neural networks? Now's a good time to clarify any conceptual understandings, because we're going to see more details in how these actually work. Yeah? Yes, so here we have a weight matrix, and so essentially in your weight matrix, you have a row associated with every hidden unit. So this H1 is a vector of, let's say it has 64 nodes in this hidden vector. We have one row in my weight matrix associated with every one of those 64 hidden units. To get the value for the first hidden unit, you take your X vector, you multiply it with the weights in the first row, and sum them all up. So it's like a dot product. That gets you a single number, like an unnormalized sort of score for the first hidden unit. And then you apply your nonlinearity on top of that. And then you do this for each of the hidden units. But you can write it as a matrix vector product, so you can get kind of clean notation here. Cool. Other questions on neural networks? Okay, so let's see how you can actually implement a very simple feed-forward neural network in code. So no promises that this code actually works. You should think of it more as pseudocode. So I wrote this right before this lecture, and I didn't really test it. But here I'm just showing you can really implement a simple neural network in less than like 30 lines of code. So we'll go through what each of these lines is doing, and hopefully after this you should walk away feeling, okay, yeah, I can implement these. It's easy. So here I wrote a class called neural network. To initialize this class, I'm going to pass in a couple of arguments. So the first argument I'll use to initialize this class is the input dimensionality. So this is the number of features I have in my classification problem. So maybe I have an image, and so this is something big like 1,000. For H1 dim, this is the dimensionality of the first hidden layer. This is how many nodes I have in my first hidden layer. For H2 dim, this is how many nodes I have in my second hidden layer. And in general, these numbers don't need to agree with one another. So I might have like 64 hidden units in my first layer, and I might have 16 hidden units in my second hidden layer. But totally free to choose these. These are hyperparameters of my model, and I can just kind of pick these at will. And then I'm also going to specify the number of classes in my classification problem. So maybe I have 10 different classes in my problem. And you can think of n classes as sort of how many nodes I have in my final layer, how many outputs I have from my network. So this is initialization. This is all I need to specify my sort of model architecture. Okay, so at initialization, what I'm going to do is I don't know what the weights and the biases are in my network, so I'm just going to randomly initialize them. So these first lines here are the weights and biases just in the very first layer of my network. So I have a single bias value, and my weight matrix, W1 in the first layer, is going to be a matrix with H1 dim rows and input dim columns. So it's essentially just a weight matrix that has the appropriate shape such that I can multiply it with an input vector of length input dim and get an output vector of length H1 dim. So it's like a mapping from a vector with input dim entries to a vector with H1 dim entries. So just a weight matrix with the appropriate size. I do the exact same thing for the second layer. Of course, these are new random values. These are new weights occurring in my second layer of my network. Except now I'm not mapping between the input dimensionality and the first hidden dimensionality. I'm mapping between the H1 dimensionality and the H2 dimensionality. So I'm going from the sort of shape in my first hidden layer to the shape in my second hidden layer. And then, of course, we also have weights and biases associated with sort of the readout layer of my network, the very final layer of this network. And so this is going to be a mapping from the H2 dimensionality into the number of classes. So again, just setting up giant random weight matrices here. Here, we're not really going to look in the details of how you learn these networks. I'm just showing you how to implement sort of the forward computation, how you do predictions. Implementing backprop is something that's a little bit too in the weeds for a quick demonstration. So, okay. In this next function here, I'll call it forward. And in this forward function, what it does is it takes a data point, x. So here, x is going to be a feature vector having should be input dim entries in it. So it's just some feature vector. And it's going to pass it through my network, each layer at a time. And at the end of the day, it's going to return a prediction for this vector. So it's going to predict those class probabilities that we saw. Okay, in the blue box here is the computations needed to compute the hidden units in the first layer of my network. So to get the sort of pre-activations, as I'll call them, these are essentially the unnormalized hidden unit values. I'll call them H1. I just do a matrix multiplication. So you can do this in NumPy in just one line, numpy.matmul. I'm going to multiply my weights in my first layer times my input x. Then I'm going to add that bias to it. So this is just that linear function of my inputs to get the sort of pre-activations in the first hidden layer. Then, of course, I need to apply my activation function on top of those hidden unit values. So in this case, I'm going to use the ReLU function as my nonlinearity. In terms of math, what's going on is this equation down here. My first hidden unit, all the vectors in my first hidden layer, is my nonlinear function. Here, the ReLU function applied to this matrix multiplication plus my bias term. So that's this math implemented in 2 lines of code down here. I'll do the exact same thing for the second hidden layer. I'd like to point out here that I'm sort of computing all of my hidden values simultaneously using this idea of vectorization. So I don't have to write a for loop to compute each hidden vector node individually. I just do it in one shot using NumPy's vectorization. And in terms of math, what's going on here is that it's the same exact idea. It's a matrix multiplication between the weights in my second layer, but now I'm applying it to the values in the first hidden layer rather than applying it to the actual data itself. So that's sort of propagating through this network. And at the very end of the day, I need to take my second hidden layer and turn it into output probabilities. So I'll do this in the exact same way. I'll multiply my weights in my final layer, these betas, with this second hidden unit, add my bias term, and at the very end of the day, rather than using a ReLU as my activation for the final hidden unit, I'm going to use the softmax function. So the softmax function takes this vector out of unnormalized scores, turns it into a probability distribution over the classes. Okay, so that's it. We've seen our first neural network in code. Hopefully you should agree, relatively straightforward to do. So any questions on this implementation? Yeah. ReLU is an activation function, and we'll see it on the next slide in some more detail. Yeah, another question. Yeah, so the question is, H1 and H2 are hyperparameters. How do we pick these? Yeah, we'll see a lot more detail on how to do that in the rest of today's lecture. In practice, it takes a lot of hard work to figure these out. Yeah. Okay, so I kind of glossed over some details of things I used in this implementation, and I'll just show you how you can implement these in 1 or 2 lines using some NumPy trickery. So this ReLU function someone asked about is the activation function I'm using in my neural network. So we saw this before. It's this function that takes in an input, and if that input is positive, returns the input. And if that input is smaller than or equal to 0, it's just going to return 0. So it's this kind of like hinge-shaped function, if you like. This is going to be the activation function we use in our network. This is our nonlinearity. And you can implement this in just 1 line using NumPy. And in fact, you can implement this in a vectorized way. So you can apply this to not a single value z, but a whole vector of value z, kind of in one shot. And to do that, I'm using this function from NumPy called minimum. So it takes in a vector of value z, so z is just some list of numbers. And in numpy.minimum, if I call this with z and 0, is going to do exactly this. It's going to change every entry in z to be the minimum of z or 0. So yeah, I've got this ReLU function just in a 1-liner and vectorized, so very clean. And then the other thing we need to actually implement our network is this softmax function. So we've seen this before in the context of multi-class logistic regression. It's the activation function we use in the output layer of our network. And the way we get this softmax is that we exponentiate all of our sort of scores. So these are the unnormalized outputs in the final layer of my network. So showing you what's going on here, this first line out from sort of that neural network class is the weights beta applied to the final hidden layer plus a bias. So these are the sort of unnormalized scores coming from the network. That's exactly what these z values are going to be here. These are the unnormalized outputs of my model. And again, we want to turn these into probabilities, so we need to make them positive and sum to 1. So we make them positive by exponentiating each of these, and we make them sum to 1 by just dividing by their total sum. We can do this in 2 lines using NumPy again. We can just exponentiate every value in a vector z by just doing numpy.x on z. So this is vectorized. It computes the whole thing in one shot. And then we just essentially implement this softmax function by taking xz and dividing it by the sum of the entries in there. So, fairly straightforward to implement softmax if you're comfortable with these NumPy functions. Okay, and so I've said this a bunch already, but I really want to emphasize the importance of vectorizing computations here. So you could do all of this kind of 1 entry in your vector at a time using for loops, but this is going to be painfully slow. So it's really important to get comfortable with vectorizing these operations, doing things sort of on multiple inputs at the same time using these nice built-in NumPy functions. So this network that we've implemented is pretty small network, 2 hidden layers. You of course could essentially take this calculation that we did here and just repeat it for an arbitrary number of layers. So straightforward to turn this 2-layer network into a sort of arbitrary depth network. And there you go. You've got sort of an arbitrary feed-forward neural network in only a few lines of code. Of course, you don't want to implement these things yourselves because there's nice libraries out there that actually have them implemented and working, and probably have less bugs than code that I could write. So if you want to see how to sort of import an equivalent network in scikit-learn, which is what you'll be doing in parts of the second homework, you can just import this model from neural network called MLP classifier. So this is a feed-forward neural network. And then we just instantiate one of these objects. I'll call it NN. And I give it a list of hidden layer sizes. So to specify sort of the architecture of a network in scikit-learn, you specify a list of the hidden dimensions. So in our case, it would be H1 dim and H2 dim because we have 2 hidden layers. And then I specify I'm using the ReLU activation function. One thing you'll notice is that in the scikit-learn implementation, I didn't need to specify the input dimensionality or the number of classes. And this is because in scikit-learn, it'll automatically infer these things from you when you go to train the network. I mostly include them in here just to illustrate where they're actually appearing in the sort of network architecture. Okay, so maybe pause here. Any questions on the implementation? Yeah. In general, you don't want to do anything other than softmax for the output of your network for classification problems. But yeah, a lot of sort of modern machine learning, or deep learning research at least, is just people being creative and clever about how they wire these things together. So if you have some crazy idea of how you want to set up a neural network and try it out and see if it works, then go for it. Maybe you've got the next award-winning architecture or something. So, cool. Other questions on the implementation? Okay. So in the first problem of homework 3, you're essentially going to be computing this forward pass on a neural network, except we're going to ask you actually to do it by hand rather than implementing it in code. Sounds a little painful, but it's a small network. It's only got two hidden vectors, only a single hidden layer. And I think really doing it by hand will sort of, really make sure that you know how these forward pass operations are working. So we give you an input X, we give you a weight matrix W, and we give you a sort of readout weight matrix beta, and your job is to just do this forward pass computation. So feel free to check your answer in code, but do actually do it by hand. Okay, so in the last part of today's lecture, we're going to talk about how you actually tune a neural network in practice. So how do we pick hyperparameters? How do we pick model architectures? How is this done actually sort of in practice? So as we've seen, neural networks, as compared to something like KNN or like nearest centroids, have a ton of hyperparameters. So for example, you might have a regularization parameter in your network helping you fight overfitting. So you might want to tune that sort of regularization strength. You might also want to tune the type of regularization you're doing. Do I want to do L2? Do I want to do L1 regularization? You've also got hyperparameters associated with your optimization algorithm, so something like the learning rate in gradient descent. If you're doing stochastic gradient descent, you might want to look at tuning the batch size, so how many examples you look at a time. These sort of optimization algorithms have their own set of hyperparameters you can play with. And then, of course, there's the sort of network model architecture itself, so how many layers do you have? What's the size of the layers? What type of nonlinearity do you want to use? So on and so forth. So as you can see, this kind of gets out of hand very quickly, and so picking the right values for your hyperparameters is pretty challenging. And I'd like to point out, just briefly, it's something you should keep in mind when you're tuning these networks is that more layers and bigger layers is going to lead to more complex models. And we'll see why that's sort of important to keep in mind in the next few slides. So there's really sort of a fundamental trade-off between model complexity and model performance in pretty much all machine learning models. But I think this is really emphasized in neural networks. So as your model gets more and more complex, has more hidden units, more layers, more parameters, it essentially will be able to fit any training data you give it perfectly well. So I mentioned that there's this theory result that says if you make your network big enough, it can represent any smooth function. So with enough parameters, we can do basically anything we want. But this is with the caveat that it only can fit the training data perfectly, and its performance on test data, which is what we really care about, data our model hasn't seen before, is eventually going to start decreasing once we start overfitting to our training sets. So for neural networks, you should think of, again, the sort of size, the number of parameters, the number of layers as capturing the complexity of this model. But of course, this trade-off, as we've seen a few times, is not limited to just neural networks. So graphically, on the x-axis in this plot here, we've got something like model complexity. So for example, it could be like number of parameters in a neural network. And on the y-axis, we've got classification error. And what we sort of optimize in reality is this training error. So we make our model better and better on the training set as we increase the model complexity. But eventually we'll start overfitting, and even though our testing error decreases for a while, up to a point, eventually our model is so complex that it's just memorizing the training data, not really learning anything useful. And again, what we really care about is this testing error. Who cares if our model memorizes the training data? I could give you a model that gets 0% error rate on the training data by just returning the training data to you, no learning. So we really want our models to be able to generalize to new data points. On sort of the left-hand side of this figure, when your model is not very complex, this is this underfitting regime again, your model is too simple to fit the data, so it's doing poorly on both your training data and on your testing data. And on the right-hand side of this figure, we have the situation where our model is too complex, we're in this overfitting regime. So our model is too big, it's perfectly memorizing the training data, but not generalizing to new data points. And the ideal model complexity is somewhere right in the middle, where we get sort of the minimal error on our training data, or testing data, sorry. So I'd like to introduce a concept here called bias variance and sort of this trade-off between them. So when I say the bias of a model, what I mean by that is how good our model is at approximating sort of the true decision boundary for our problem. So something like a nearest centroid classifier, if you'll remember, is a model that has very high bias in the sense that no matter how much data we give a nearest centroid model, it can only learn linear decision boundaries. So it's a very simple model, it has high bias. You know, it kind of can't get better than its limitations. And the other concept here is the variance of a model, which is the sort of sensitivity of a model to different data set sizes or different sort of random data sets. So imagine if I had a data set with 1,000 training points in it, and I randomly took two subsets of that training set. So I took 100 points and I took another 100 points. If I trained two models of the same sort of architecture on those smaller training sets, the variance captures how different those two models would look. So for a nearest centroid model, if I train it on two small data sets coming from sort of the same data distribution, it's going to look like pretty much the same model. It's not very high variance. It doesn't take a lot of data to learn it. But on a neural network, for example, if you train a network with 1 billion parameters on 100 data points, well, if you have two different really small data sets, your neural networks are going to look a whole lot different from one another at the end of the day. So they're high variance in the sense that they can sort of vary a lot depending on the training data you have available to you. And there's this really classical result in machine learning, which you can sort of prove theoretically in a very rigorous way, which is that your testing error is actually a function of the bias plus the variance. So what this means is that there's actually a sort of fundamental trade-off between these notions of bias and variance. So you can have a low bias model, so a model that can have very complex decision boundaries, but this model is necessarily going to have high variance. You know, it's going to change a lot depending on the training data we have. In contrast, a very simple model might have high bias, something like a nearest centroid classifier, can only fit very simple decision boundaries, but it's going to have lower variance. It's going to take less data to learn, and it's going to essentially be a little bit more robust to small data set sizes. So I'll spare you guys the math and won't go through sort of proving that this actually works out, but it's a very good concept to keep in mind, this bias variance trade-off. So in terms of this sort of graphical illustration we had before, as you increase your model complexity, more parameters, just more complicated models in general, the bias of your model is going to decrease. It can learn more complex decision boundaries, but the variance as a result is going to increase. Because we can have more complex decision boundaries, it's going to be sort of more sensitive to our data. So ideally, we would like something that has low bias and low variance simultaneously, but of course, this is something we can't always achieve. So in the homework, you'll actually be exploring this bias variance trade-off a little bit. So in problem 2.2 on the homework, you're going to actually be reproducing this figure below. So in this figure, what we have is on the x-axis the number of data points that a model was trained on. So this is the training data set size. And on the y-axis, I have the classification error rate. So ignore the solid lines. Let's just look at the dashed lines for the time being. The orange-yellowish line is the testing error for an MLP, so for a small neural network. And the blue dotted line is the testing error for a logistic regression model. And what I'm going to argue that this figure really illustrates is that logistic regression models, have a high bias but a low variance. And in contrast, neural networks have a low bias but a high variance. So let's look at this first data point here, where we're training our models on only 100 data points. What you should notice is that our neural network model gets an error rate of like 40%, and our logistic regression model gets an error rate of like 32%, let's say. So the logistic model is actually doing better than the neural network model when we have a small data set size. Okay, this is interesting because our neural network model is a whole lot more complex than a logistic model, right? But this illustrates that our logistic model has low bias in the sense that it only takes a few data points, here 100, in order to learn a pretty decent model. But if we look on the right-hand side of this figure, we see that if we give our models more and more data, so say up to 1,000 or 10,000 data points, eventually our NLP, our neural network, overtakes the performance of the logistic model. So given enough data, a neural network can learn a very complex decision boundary that is going to do pretty well on this problem. In contrast, no matter how much data you give this logistic regression model, its performance kind of saturates. It can only learn linear decision boundaries, and so no matter how much data you give it, it's just not going to be able to learn sort of those fine-grained details it needs to. And this right-hand side of the figure really demonstrates this idea of bias. Logistic models are biased in the sense that they have very limited decision boundaries that they can learn. And in fact, if you gave your neural network model even more data, this line probably would decrease even further. So neural networks, very low bias, but very high variance, and logistic models are kind of on the other side of this coin. So yeah, if you manage to do this problem in the homework, you hopefully should see more or less exactly this figure. Okay, so we haven't talked yet about how you tune hyperparameters in neural networks, and that's what we're going to be focusing on for the remainder of today's lecture. So just a couple of pieces of kind of practical advice. As we mentioned, more complex models always are able to better fit your training data. They just can essentially memorize more of your data. So it's important to always use your validation set as the means for selecting and comparing models. It's a pretty common mistake that people make is that, looking at training set error to do model selection, and you definitely don't want to be doing this. It's a good idea, if you're working on sort of a real-world machine learning problem, to include a relatively simple model as a sort of baseline to compare to. Oftentimes people like to reach for kind of the fancy, high-tech tools, neural networks. This often isn't really necessary, so it's good to at least try like a logistic model or a KNN. Maybe this is good enough for your problem and you don't even have to worry about tuning a neural network. In contrast, or rather another point here is that if you have a large data set, it might be more appropriate to reach for a more complex model. And conversely, if you have a very small data set, probably the first thing you should reach for is a very simple model like logistic or KNN. And in general, if you're working with a really small data set in machine learning, be very careful. It's very easy to overfit to these small data sets. So for instance, this often happens in, say, like a medical application where you only have a data set of like 100 patients. Well, you don't want to fit a neural network with 1 billion parameters to this data set, you're just going to be overfitting. And it's good to keep in mind this concept of regularization that we've seen a few times by now. If you see that your neural network model is overfitting, then regularization can be a very handy tool for preventing this. So I've shown you guys this figure before, but I really like this analogy. So your sort of everyday model, your Toyota Corolla, is really great for sort of driving to and from the grocery store, getting around town and running errands. This is your everyday car. You use this for most tasks that you care about. Something like a Ferrari is great if you want to, say, take a drive up to the bay for the weekend. You want to get there pretty quick. You want to speed down PCH the whole time. It's great for those kind of niche purposes. So this is something like a small neural network. And then these very large, very deep neural networks are more like a battleship. So they're a whole different class of their own. And of course, it's really not appropriate to be driving your battleship to the grocery store. You're probably not going to find a parking space. But they're great when you really, really need them. So it's good to keep in mind that even though neural networks are very popular, very fun to work with, most of the time you're going to be happy with the logistic model or KNN or something like that. Okay, so let's talk about tuning neural networks with that caveat as a warning that you don't always want to bother doing this difficult hyperparameter search. So remember that we use this kind of train, validation, test paradigm. So you take your original data set and you split it into 3 different subsets: a training set, a validation set, and a testing set. And the idea is you train your models on your training data, you evaluate their performance on the validation data. Whichever model is doing best on this validation data is sort of your final model. It's the one you're going to choose to deploy out in the real world. And then you'll eventually test it on some third held-out testing data set. In practice, sometimes machine learning people can be a little bit lazy with this and not have a third held-out testing data set. And there can be a little bit loose terminology between validation and testing. But if you really want to do things the proper way, you should have these 3 different splits. So the most basic, straightforward way of doing hyperparameter selection is via a grid search. I'll take questions in a minute. So a grid search, what I mean by that, is you specify sort of some ranges of values for each of your hyperparameters. So maybe your first hyperparameter is the depth of my network, and the second hyperparameter is the width of my network. And then I just try every possible combination of these hyperparameter values, fit the corresponding models on my training data, evaluate them on a validation data set, and then pick the best values. So here I would, here's exactly that procedure, but in words. And so here I would test out a total of 9 different models, trying out each of these possible combinations of hyperparameters. One problem with doing grid search is that it's very expensive to do this and can be very time consuming. So if you have D different hyperparameters that you're trying out, and each of these hyperparameters takes M distinct possible values, well, you've got M to the D different models to be training in order to do this grid search. So it's exponential in the number of hyperparameters you're testing. For a neural network where it can take 5-10 minutes to train a really small network even, this is just not going to be feasible to do unless you're Google or Amazon and you have like 1 million GPUs to train these models on in parallel. So grid search, very simple, kind of the brute force way of doing hyperparameter selection. An alternative is that you could do something called random search. So one drawback of grid search, beyond sort of just the computational infeasibility of it, is that you don't really know when you're setting your problem up what the important hyperparameters are, like which ones are going to affect model performance the most. And you don't really know what values of these hyperparameters are going to lead to high accuracies. If you did, you would just pick them from the get-go. And so what can happen is if you don't make your grid kind of fine enough, you don't look at enough hyperparameter values, you might kind of miss the region of high accuracy in the sense that these hyperparameter values in this yellow region might get missed by your grid. You can do something kind of interesting called random search as an alternative method. So rather than setting up a grid of hyperparameters and trying out all the possible values, you just randomly select hyperparameters in sort of the ranges that you choose. So rather than, again, doing a grid, I just randomly select these, maybe uniformly from their ranges. And this has 2 benefits. The first is you're kind of more uniformly exploring the design space. So you're trying out a whole bunch of hyperparameter values you might not have seen during your grid search. And in essence, you end up getting sort of a better coverage, a better sampling of the possible models you could try out. Another benefit here is that with grid search, here I'm only trying out 3 different values for each of my hyperparameters. I'm trying out this value, and this value, and then this. But of course, I'm trying out the different combinations, so I train 9 different models in total. In contrast with random search, every new parameter vector that I choose, every new hyperparameter that I choose, is a totally new combination. So here I'm trying 9 different values for each of the hyperparameters, as opposed to 3 on the left-hand side. So again, you can kind of get a better exploration of the space. Okay, so yeah, there's a question earlier. Yeah.
So for test, would you then retrain the model on the training and validation data for the final test? When you finally pick the right model?
Yeah, so the question is, what do you do after you pick your model on the validation data? And yeah, probably the best thing to do is choose the hyperparameters that did the best on the validation data, fix those, and then train on your training and validation data combined. More data is always better. If your validation set is small, but yeah, you could do that. Yeah, another question. No, this is just for illustration purposes. I mean, in practice, you don't know what the important hyperparameter is, and you don't know what the unimportant hyperparameter is. It's just kind of to illustrate that your model is very sensitive to this parameter, but not very sensitive to this hyperparameter. And so it's kind of wasted computation to be doing this exhaustive search over the second hyperparameter here. Yeah. Okay, maybe do one more question. Yeah. Exactly, yeah. If you're being a good machine learning practitioner, once you look at your testing data performance, you're done. That's your model. The idea being like, maybe your boss is not a machine learning person. CEO of your company says, okay, great, you trained your model. How's it going to do on new data coming in? And you say, okay, I've got my model. It's fixed and trained. It's going to do approximately this good on the testing data that I'll see later on. So it's kind of the very last step of your model, and you would say, yeah, I'm going to write this number up in my report. Okay, so I can take more questions at the end, but I'd like to get to some tips for homework 3 at the very end here. So in the last problem of homework 3, 2.4, it's your job as machine learning practitioners to go ahead and actually tune a neural network. So your job here is to get a validation error rate of smaller than 5% on the MNIST dataset using a neural network. So this is actually not all that straightforward. If you just try out some random hyperparameter values, it's probably not going to give you less than 5% error rate. And so if you're unable to solve this problem in a reasonable amount of time, I don't want you to spend like 40 hours trying to get this error rate, you can receive pretty much all the credit for this problem by trying at least just 10 different hyperparameter settings. So if you can't quite figure this out, no big deal, you can get most of the credit for the homework. And just a reminder, MNIST is this handwritten image data set problem, so it's a 10-way classification problem. So if you look at the documentation for scikit-learn's neural network classifier, just looking at sort of the signature of this function, there's so many hyperparameters here, right? There's activation functions, hidden layer sizes, so on and so forth. So like, how are you supposed to even approach this problem? And even worse, training neural networks is really slow. So even on this small MNIST data set of tiny images, exhaustive grid search, just trying out every possible hyperparameter and every possible value you can think of, just not going to be feasible. And so you should really use these notions of overfitting and underfitting to help you guide your sort of search in sort of a smart way. So again, this is the figure you should keep in mind for problem 2.4 in the homework. And again, you can assess overfitting and underfitting using this kind of decision matrix. So if you have high validation and high training error, you're underfitting, your network isn't complex enough. If you have high validation error but low training error, then you're overfitting, so you're in this too complex regime. And for all intents and purposes, you can ignore the bottom row here. But you can use this idea to sort of iteratively assess model performance. And what I mean by this is, for example, you might just try some initial random guess for the hyperparameters of your network. Maybe you try the defaults in scikit-learn. Maybe they're defaults for good reason. Then you can look at your model performance on both the training and the validation set and sort of assess whether or not this model that you chose with these particular hyperparameters is overfitting the data or underfitting the data. If you see your model is underfitting the data, then okay, what hyperparameter should I play with to make my model more complex? I want it to be able to better fit my data. If you see your model is overfitting to the data, well then I need to reduce the complexity of my model, right? It's memorizing the training data but not generalizing. So I need to do something like make the network smaller or change some other hyperparameters or maybe try regularization. So again, I like to emphasize, don't just try random hyperparameter values. Really think about what your model performance is telling you. It should hopefully save you guys quite a bit of heartbreak on trying to tune these. So let's see, in the interest of time, let's wrap up in about 30 seconds here. So this really ends our discussion on feed-forward neural networks. We've seen both the theory and sort of the practical details of setting these up and training them. Again, these are very complex, large models, and they're most useful for problems with big data sets. But again, not appropriate for all classification problems, especially if you have small data sets. And really, these are just an extension of this logistic model that we saw, where we now sort of stack multiple logistic models on top of each other. Tuning these models is difficult, but it's very good to keep in mind this overfitting and underfitting idea.